Okay, welcome back, and we're going to start looking at spontaneity and Gibbs free energy. So Gibbs free energy is the last piece of this puzzle that helps us predict whether or not a reaction will be spontaneous based on thermodynamic data. So as we talked about before, we've seen a number of spontaneous reactions, but we haven't really talked about what makes a reaction spontaneous at the chemical level. We've seen that it can be heat energy released as the reaction proceeds for an exothermic reaction, or it can be because the system is becoming more disordered, having a positive entropy, or it can be a combination of enthalpy and entropy if we look at the overall change in the universe of the entropy or the surroundings, as we talked about before. This can seem like there is no consistency, but there is. One way for us to start to get our heads around this is to look at the Haber process again that we looked at in equilibrium. So if we consider the reaction that produces ammonia being the Haber process, we have N2 plus 3H2 is an equilibrium to 2NH3. If we have a look at this, we know that from the enthalpy, this is an exothermic reaction, and we can calculate it under standard conditions to get the enthalpy of the reaction using the enthalpy of formation of the reactants and the products. Remembering that we're going to have products minus reactants, and in this case, the reactants are both going to be zero because we have elemental nitrogen and elemental hydrogen, so these are going to be zero, which means that we'll just get 2 times the enthalpy of ammonia, which is going to give us negative 92.6 kilojoules per mole. So we know this reaction is exothermic, and we can look at the entropy of the system, however, and we can see that we have 4 moles of gas going to 2 moles of gas, which would indicate a decrease in entropy. And if we calculate this from the sum of the entropies of the products minus the sum of the entropies of the reactants, we can see that in fact this is what we get. We get a negative entropy value of 198.5 joules per Kelvin. So the entropy of this reaction is not favorable to it being a spontaneous reaction, and it can be seen qualitatively by noticing that the reaction has 4 moles of gas reactants going to 2 moles of gaseous products. So we could see that it would be a significant increase in order and a decrease in disorder. So in this case of a well-known reaction that we've seen multiple times, enthalpy and entropy disagree as to whether or not the reactions should go ahead, because enthalpy says yes, but entropy is saying no. This is where we need to look at it in more detail, and we need to understand the energy and the energetics of the system a little bit more. Gibbs free energy, which is given the symbol G, one of the most sensible in energetics, is calculated from this reaction here. Delta G is equal to delta H, the enthalpy, minus the temperature multiplied by the entropy. Gibbs free energy is defined as the energy available to do work. So this is often considered the driving force of the chemical reaction. It's not a force, it's a tendency due to thermodynamics, okay? So it's not a quantifiable force. Where enthalpy gives us how much energy is around, Gibbs free energy is basically telling us what part of that energy can be used for work and not just lost as heat. It's calculated by combining enthalpy and entropy, with the temperature also being a part of this reaction. So it's used to determine whether or not a reaction is spontaneous. So delta H is given by the total change in energy, the heat of reaction. It's the total energy change at a constant temperature for a reaction. Delta G, however, is the free energy available to do work, and T delta S is basically the energy tied up not available to do work. It's tied up in increasing disorder. So the delta H is the drive towards stability. So when delta H is less than 0, the products are more stable. They have a lower enthalpy than the reactants. When delta S is the drive towards disorder, delta S is greater than 0, the products are more disordered than the reactants. increasing temperature increases the influence of delta S on the reaction's driving force, because remember, increasing temperature will always increase the entropy. So this will increase the effective entropy on this balance of the energy in the system. Temperature is always used as Kelvin for calculating delta G. So delta G is our energy available to do useful work. So there are two ways that we can calculate delta G. We can use table 12 from our data booklet, and it gives us the delta G naught for set products and reactants. Okay, so again, just like delta H and entropy, this is products minus reactants. We sum up all the Gibbs free energy of the products and we subtract this Gibbs free energy of the reactants. Or we can use the equation that the Gibbs free energy is equal to the change in enthalpy minus temperature times delta S. So delta G is equal to delta H minus T delta S. If delta G is negative, i.e. it is less than 0, the reaction is spontaneous. If it is 0, the reaction is at equilibrium. And if it is greater than 0, the reaction is non-spontaneous. Okay, so delta G negative is a spontaneous reaction, delta G 0 is a reaction at equilibrium, and delta G greater than 0 is a non-spontaneous reaction. So showing this on a graph, we can see that delta G positive, a spontaneous change is impossible. Delta G negative, a spontaneous change will be possible. This graphic shows us the influence of enthalpy versus the influence of entropy on whether or not a reaction will be spontaneous. Remembering delta G needs to be negative to be spontaneous. So if delta H is less than 0, delta S is greater than 0, it will be spontaneous at any time. Remember, delta G is going to be equal to delta H minus T delta S. So if delta H is negative, and I'm going to be subtracting a large positive value, this will always be negative. So it will always be spontaneous. And it doesn't matter what the temperature is, because all I'm going to do is increase or decrease this. Delta H being less than 0, delta S being less than 0, it will be spontaneous at low temperatures. So if delta G needs to be negative, and I have a negative delta H, I'm going to be subtracting a negative delta S, but as long as T is small, then I shouldn't add a value high enough to make this positive, so delta G should stay negative. If I have a positive delta H value and a positive delta S value, then there is no way that this equation can end up negative. Okay, other than if this is at very low temperatures. Okay, so what we want to do, this will be spontaneous at high temperatures because we will subtract a large value for delta S. The opposite is true if I have a positive delta H and a negative delta S. This means that positive delta H minus a negative is always going to be positive. So I'll be adding T delta S. There is no way that this can ever be spontaneous because I'll always have a positive solution to the mathematical equation. So again, we mentioned that delta G can also be calculated for reaction using delta G products minus reactants. It is equal to 0 for any element in its most stable state. Okay, so we can see here that chlorine gas is its most stable state. Delta G will be equal to 0. Hydrogen gas, 0. This is not the same as enthalpy. These values are 0 for the most stable state of these elements. Okay, this may not necessarily equate to their standard state. You can see here gas and liquid water still have a negative delta G value. So compounds that have a positive delta G are less thermodynamically stable in their constituent elements. So they can't be synthesized from their elements as there is a tendency for them to convert back into it. Okay, In practice, compounds such as benzene are still often kinetically stable because of the large energy barrier to their decomposition. Okay, so remembering that benzene has that extra stability provided by the delocalization of the pi cloud. Okay, last couple of things. Delta H and delta S are independent of each other. Okay, so they're not linked. They will influence delta S can be influenced by temperature, but enthalpy and entropy are independent of each other. You can have situations where both will be positive and both will be negative, or one is positive and one is negative. The direction of one does not influence the size or direction of the other. They do, however, influence whether or not a reaction is going to be spontaneous, and we need to consider both the enthalpy and the entropy of a system in order to predict whether or not it will have a negative Gibbs free energy and therefore be spontaneous. If delta H and delta S have the same sign, then they are working against each other and the larger of the two will win. Okay, entropy values are usually much smaller than enthalpy and are quoted in joules rather than kilojoules, so don't forget this difference, that your enthalpy values are kilojoules per mole and your entropy are joules per mole. So if T is increased, then the entropy term will increase as well and may become greater than the enthalpy term, but it does need to be quite significant. Okay, so couple of examples where delta G will be negative, and this therefore means that the reaction will be spontaneous. If delta H is negative, so is delta S, then this is going to be negative. This is basically a worded way of describing the graphic that we saw back here. This might be good to put in your notes once you have it set in your head as to what it means. So for an exothermic reaction with a decrease in entropy at low temperature, then delta G is going to be negative because you will have negative minus a smaller negative, so it's going to be negative. Endothermic reaction with an increase in entropy at high temperatures, you're going to have a positive value minus a larger positive value. That solution will always be negative. Where it's positive, you're going to have an endothermic with a decrease in entropy because you'll have a positive minus a negative, so this is always going to be positive. An exothermic reaction with a decrease in entropy, okay, so you're going to have a negative delta H with a negative delta S. You're going to be subtracting a large negative. This will always be positive. And then positive minus a smaller positive is always going to be positive as well. And this is what we see when we have an endothermic reaction with an increase in entropy at low temperatures. Use the grid and then see if you can annotate it with a way that makes sense to you. Remembering that essentially what we're always doing is seeing which combination will give us a negative delta G. This is an example of how you might see something being asked. In this case, we're again looking at the Haber process. We know that we have a negative delta H and a negative entropy, that these are working against each other. When we calculate delta G, we can see that we have a negative delta G, saying that this reaction will be spontaneous at 273 Kelvin or 0 degrees C. As we increase the temperature, the term for T delta S is going to become a larger negative number. When it gets greater than the enthalpy value, delta G will become positive and the reaction will no longer be spontaneous. Okay, so we can say that the temperature at which this occurs is determined looking at this, and we can test this by finding the value of delta G at 500 Kelvin. If we go delta G is equal to delta H minus T delta S, this is our delta H, minus 500 times our change in entropy, we can see that we have tipped into a positive delta G value, so the reaction will no longer be spontaneous. So what you want to have a look at is if you've been asked a question to determine the effective temperature, you're going to calculate the delta G value at the initial temperature, and then calculate the temperature at which this delta G value would become positive. Here's a couple of questions that I recommend you have a look at just to play with these equations and get them settled before coming into class, where we will look at some examples of these in exam questions. Hopefully it is starting to make some sense, and I'll see you in class.